Atomic structure is very important, and we've already talked about how things like Rutherford's gold foil experiment was able to tell that the nucleus was very dense and the protons and the neutrons were in the nucleus and the electrons kind of circled around the outside. The circling around the outside part is what we're going to focus on big time in this section, and a lot of the information that was gathered about how electrons are distributed comes from the study of light. And you can see in the fireworks animation there, and also those little flames on the left, you can have different colors depending on the types of elements inside them. Fireworks are actually an expression of this. Like you can have certain colors that are green. I believe strontium creates kind of a red color. Sodium is kind of a yellow color. If you have pure elements, they all have different colors. And you might be thinking, well, wonder where these colors come from. Well, this is what other people thought in previous decades and centuries, and then they basically slowly started figuring out what's happening. And along the way, then they also figured out more about how electrons are placed around atoms. So in this section, we're going to start talking about color, and you can't start talking about color unless you talk about light. Let's see what's happening here.
Visible light is a form of electromagnetic radiation, which emanates from the source as waves. The waves are electric and magnetic fields oriented perpendicular to each other.
Electromagnetic radiation, or EM radiation, as it's sometimes abbreviated, is a type of energy, and it's an energy that has both an electric component and a magnetic component. So you can see the red little dots right there and the kind of gray pieces. They're essentially at 90 degrees from each other. One of those is an electric field, and the other one is a magnetic field. But the important part for us now is that the light that you're using right now to see this animation, and whether the light comes from your computer or from an overhead light or the sun, all of that is a type of electromagnetic radiation. And to understand the concepts in this particular section, we really need to explore more about what light is. So this guy named Maxwell, who also has a cool beard and stuff like that, as well as James Joule from the last chapter, he was the one that really developed a lot of the theory behind electromagnetic radiation. And it's interesting because in some level, a lot of the particles, like electrons, will behave like waves. So we're going to use the knowledge of waves to understand more about electrons, particles. And this is something else we're going to get into. So in order to talk about how electrons were done, we need to talk about light. And in order to talk about light and electrons, we need to talk more about waves. So waves actually have some properties that are important for what we're going to be talking about. Waves have a wavelength, which is the distance from where the wave starts to where it stops. And this wavelength, which gets the symbol lambda right there, is truly a length. It can be measured in meters or centimeters or micrometers or nanometers, stuff like that. And I'll show you a picture in the next one. Frequency represents how many waves travel by a certain point per second. Usually it's per second. Frequency gets the symbol mu, and that looks like kind of like an italicized V, and that's fine. But frequency is literally the number of waves that go by per second, per unit time. There's also node and amplitude, which we'll talk about a little bit, but the wavelength and frequency of a wave is going to be really important to us. So let's look at a diagram which shows better what wavelengths and frequencies are all about. Here's an example of two waves. One of them is from visible light, and the other one is from ultraviolet light. And both visible light and ultraviolet light, or ultraviolet radiation, are examples of this electromagnetic phenomena that we're going to start talking about. Now, one of the things I mentioned was a wavelength, and wavelength is literally a distance, and you can measure it in meters, nanometers, kilometers, whatever. It's the distances from where the wave starts to where the wave stops. Now, because waves constantly go on and on and on, you can also say from where it starts to where it starts up again, and that's fine, but hopefully you get the idea. These waves go up and down, and before it starts going up again, that's going to be the wavelength. Notice that in the ultraviolet under here, we also have a different wavelength. It's also from where the wave quote-unquote stops and where it starts. Notice that in the visible light, it starts to go up and then down before we stop it. In the ultraviolet, we start at where it starts to go down and then up. Same thing. It's where the wave starts and stops. It's one complete wave cycle. All right, no problem. Now, the middle line, right through the middle right here, is like a 0 point. And you can consider the wave to have no basis there. It doesn't exist for a little bit. And first it goes above the wave, and then it goes below. But the points where it actually touches that line, those are called nodes. And nodes will be important. Now, a node is a natural phenomena of a wave. All right, it's a place where the wave doesn't look like it exists. All right, it does, but it doesn't exist at that particular point. And that'll be important to us later on. Amplitude, we won't talk about too much, but amplitude is essentially the distance from that 0 point position to the top of the wave. And in a lot of waves, the distance from the 0 to the top will be the same as the distance from 0 to the bottom, etc., etc. What I would like to talk about, though, is what's called frequency. Frequency is literally how many waves go by per unit time. So if you look in the green right here, I have a time equals 0 and a time equals t. And I have the same thing below for the ultraviolet. There's time equals 0 and time equals t. So notice for the visible light, we go through one wave here and about half of a wave to get to time t. So the frequency would literally be 1.5, 1.5 waves per unit time. And if that time t was a second, that would be 1.5 waves per second. Now, the ultraviolet, on the other hand, has one wave here, it has two waves there, and it even has three waves. So the frequency of this wave is 3.0 waves per unit time, or if time is seconds, 3.0 waves per second. And that's an interesting thing. So notice that one thing that distinguishes visible light, which is what we see, versus ultraviolet light, which gives us sunburn if we stay on the sun too long, one thing that's different is that definitely they have different frequencies. Ultraviolet has a higher frequency, more waves per unit time than visible light does. But also, if you look at the wavelengths, and assuming this is a comparable scale, visible light has a longer wavelength and ultraviolet has a shorter wavelength. So this leads into this part down here, which we're going to talk about more later. As the wavelength gets bigger, the frequency gets smaller. So wavelength of visible light is longer, but the frequency number is smaller. And on the other hand, ultraviolet has a smaller wavelength, all right, but it has a larger frequency. So as wavelength goes up, frequency goes down, or as wavelength goes down, frequency goes up. And those things will be helpful to us later on. There are different kinds of waves. There are what they call moving waves. Like those are the waves like at the ocean. If the waves come in from outside, they splash and they go back. Those are moving waves. Most of what we're going to talk about here in chemistry is what's called a standing wave. So imagine that you have a rope and it's connected to the wall and you decide to start rotating it. And at first you rotate it just a little bit, so it just goes up and down a little bit. But then you start moving it more and more, so you actually have more vibration, and then you really start yanking on it and you have even more. Those are all standing waves. The wave is not moving. However, you do have, for example, the wavelength, all right? So this would be one wavelength right there. You have so many waves going by per unit time. You have nodes and stuff like that. Everything we're going to look at in chemistry is basically as standing waves. We're going to see that there's ways to relate the electrons to these standing waves, which is kind of interesting.